Hello people, this week we will talk about the use of cellular automata in computational fluid dynamics to simulate the motion of fluids. Cellular automata, as you might study earlier, consist of a regular grid of cells. Each cell in the automata has some states. States are either Boolean values such as on and off, or some bounded integer values. The grid itself can be in one or more number of dimensions. For instance, here we have a 2D cellular automaton. Each square represents a cell or site. Apart from the red cells, which are in the state on, the rest are off. There is a function that determines the new state of each cell in terms of the current state of a cell and the states of its neighbors. Typically, rules for updating the state of cells are the same for each cell and don't change over time. The rules are applied to the whole grid simultaneously to obtain a new generation of the grid. Cellular automata have various applications in science and engineering to modeling and simulating physical systems. This week, we will use cellular automata in computational fluid dynamics to model the motion of gases and liquids. Next week, we will also discuss an example from the cardiac simulation in biology. Fluid dynamics is a branch of mathematics and physics concerning with the description and study of the flow of liquids and gases. It has several sub-disciplines, including aerodynamics, which study air and other gases in motion, and hydrodynamics, which is the study of liquids in motion. Fluid dynamics has a wide range of applications in industry sectors. For example, aerodynamics is vital for understanding the behavior of aircraft and other objects moving through air. It is also employed in predicting weather patterns and combustion simulation. This slide displays the Navier-Stokes equation, characterizing a fluid substance by a set of parameters, such as density, pressure, and velocity. In this equation, ρ is the density of fluid, P is pressure of fluid, and U is velocity of fluid. All are defined as functions of position. Nabla symbol here represents divergence, where the divergence of a function is equal to its partial derivatives. So, as presented here, the equation formulates the motion of fluid substances using a set of partial differential equations. As mentioned earlier, this equation describes the physical properties of fluids. It means that we can obtain how particles in a gas or liquid substance move by solving this equation. Navier-Stokes equation is analytical. Therefore, human can understand and solve it on a piece of paper. But if we want to solve this equation by computers, we have to translate it to the discretized form. For discretization, the derivatives in the Navier-Stokes equation can be mathematically replaced by finite discrete differences or by finite discrete elements. However, this approach demands lots of mathematical efforts, which is outside the scope of this module. An alternative solution is to use lattice-based approaches, such as lattice gas models and lattice Boltzmann models, to approximate the Navier-Stokes equation using cellular automata. Lattice gas model, or LGM, as mentioned in the previous slide, is used to simulate fluid flows. LGM generally uses cellular automata to simulate the flow of particles in gas substances. In this model, each cell in the automata has a set of finite states. In the following weeks, we will introduce the lattice-Boltzmann model or LBM based on LGM. The LBM simulates the kinetics of particles in gases and liquids more accurately compared with the lattice gas model. There are different approaches to implement the lattice gas model. Today we first study the HPP model as the simplest lattice gas model. HPP simulates gas and liquid motions based on a two-dimensional grid or cellular automaton. The grid is populated by a set of particles with different velocities. Each particle has an associated direction as its state. Therefore, as presented here, the blue arrow highlights a negative movement along x-axis to the left. Similarly, we have three other movements highlighted as state 1, state 2, and state 3. As we can see here, particles cannot move diagonally. In this model, particles' directions might change because of interact with other particles in their grid. In other words, once a collision occurs between two or more particles, their directions might change. However, interactions don't impact the velocity of particles in terms of magnitude. We will study collision later on in this presentation. This slide presents a small-scale demonstration of the square lattice HPP model. In this model, we have a two-dimensional lattice populated with a few particles. As shown here, the direction or state of particles doesn't change unless they involve in an interaction. Now, we want to computerize the HPP model based on 2D cellular automata. In HPP, a 2D grid consisting of several cells models a lattice. At any given time, there is at least one particle at any cell in the HPP automata. As mentioned earlier, these particles can be in one of the four states, 0, 1, 2, or 3. So, the local cell state can be modeled by an array of four Boolean variables. This array is named flog, as shown here. Flog 0 is true if there is a particle in the cell in velocity state 0, otherwise false. Flog 1 is set to the true if there is a particle here in velocity state 1, otherwise it's set to false. Similarly, flog 2 and flog 3 are set to true if there is a particle in the cell in velocity state 2 or state 3 respectively. As mentioned in the previous slide, array flog determines the state of a particular particle. Each item in this array is a Boolean variable having values 0 and 1. Based on this, the local density of a particle is defined as the summation of all four elements in flog. In cellular automata, the new state of each cell is determined according to some fixed rules, which are generally mathematical functions. By applying rules to all cells in an automaton, the next generation of cell states is computed. In real applications, all cells in a grid are initialized to random states. Then the rules or functions are applied several times, say several thousand iterations, to simulate the understudy problem. In HPP, there are two steps for computing the next generation of cell states. Using these rules, we can simulate the motion of particles in a grid. The first rule is collision, followed by the streaming step. Both sets of rules must be applied to any cell in a grid in order to compute the next generation of cell states. In the following slides, I will go through each step in detail. Let's start with the streaming step because it's rather simple. In this step, if there is a particle in a particular direction at a particular site, it moves one step to the next site in that direction. For instance, here we have three particles, each with a particular state. After applying the streaming step, each particle goes forward one step to the next site or cell. In the streaming step, the state of particles doesn't change. In other words, the velocity of particles remains unchanged after this step. In this slide, we learn how the streaming step updates the local state array of cells in the grid. Suppose f(x, y) is an array determining the state of a cell in position x, y in an automaton. Let's f(x, y) out determines the local state of a cell located in position x and y before streaming. And f(x, y) in represents the final cell states after streaming. Based on this definition, the streaming step updates the cells as shown here. The first rule implements negative movement along x-axis. For instance, if there is a state 0 particle at cell 2 and 1, it moves to its neighbor cell at position 1 and 1 after the streaming step. The next rule moves a particle in state 1 to its right neighbor in the grid. Here we have a particle in state 1 located at x equal to 0. After streaming, the particle will be at x equal 1. Similarly, the two last rules perform movements along with y-axis in negative and positive directions, respectively. In the following slides, we can see how the streaming step creates new generations of cell states by example. In this example, we have three particles as shown here. The local state array of each cell hosting the particles is shown beside the cell. This slide shows the local state arrays of cells after one streaming step. Here we have the next generation of the cell states after another streaming step. And movements after another streaming are presented in this slide. After a streaming step, the incoming particles at a particular site can interact through a collision, as shown here. In this situation, more than one particle resides in a single cell. However, in cellular automata, it is supposed that each cell hosts one particle at most. Therefore, we must apply collision rules to determine what happens if multiple particles reach the same site. Based on the collision rules in the HPP model, two incoming particles involved in a head-on collision are deflected perpendicularly. It should be noted that deflection moves a particle to an unoccupied cell. This way, collision rules prevent two or more particles from occupying one single cell. In addition, I want to highlight that the collision rules only change the direction of partitions, while the velocity magnitude remains unchanged. This slide presents how the collision rules work for some head-on interactions. In the first two cases, two particles are involved in a head-on interaction. But based on collision rules, these particles are deflected perpendicularly. In the last case, we have a collision between three particles. As we can see here, after applying the collision rules, it looks like no change happens in the direction of particles. In this slide, I want to present the pseudocode implementing the collision rules in the HPP model. The first if clause simulates the first collision discussed in the previous slide. As we can see here, the two particles in states 0 and 1 are reflected with new states 2 and 3. Next if block deals with the two particles hitting together vertically and updates their states to 0 and 1. Apart from the two cases discussed in the previous slide, collision makes no changes on the velocity of the particles in the other possible cases. It's noteworthy that the particles can hit together in a particular cell in 16 possible cases. It is because the local state array F for each cell consists of 4 elements. Each has 2 values. So there are 2 to the power of 4 possible arrangements for particles in a particular cell. Although HPP is able to simulate some features of realistic fluid dynamics, its output cannot accurately describe the motion of fluid substances as formulated by Navier-Stokes equation. To address this problem, in 1986, another simulation method named FHP was introduced. This model works very similarly to the HPP, but it is defined on a triangular lattice instead of a square one. Here we have a triangular grid where each cell has 6 neighbors. In the following slides, we revise streaming and collision rules in the HPP model to make them suitable for 6 neighbors. In the FHP model, each cell has 6 neighbors rather than 4 in the HPP. So, as shown here, there are 6 states instead of 4 in the local state array F-log. Apart from this difference, the streaming step works in exactly the same way as discussed in the HPP model. Let's now go through the collision rules in the FHP model. Here we have some examples demonstrating the collision rules in the FHP model. The first case shows a two-particle head-on collision. Using the collision rules, the current states can be transformed into one of the two different states, as presented here. In this case, the particles are first rotated by 60 degrees to either the left or the right, and their directions are reflected. The choice between the two different states will be made by a random process with equal probabilities for rotation to the left and to the right. So, in contrast to HPP, the FHP model encompasses non-deterministic rules. There are deterministic final states when three particles involve in a head-on collision. As we can see here, the directions are reflected. The next case shows a two-particle head-on collision with a spectator. These two particles will rotate by 60 degrees while the spectator state will remain unchanged. The final states for double head-on collisions can be computed by a 60-degree rotation of each particle to either the right or the left. Like the first case, this collision leads to two possible outcomes, and the outcomes are chosen with 50-50 probability. As you might recognize so far, implementing collisions in the FHP model is a little more complicated compared with the HPP. It is because there are totally 64 possible cases to consider in the triangular lattice. If we consider all the 64 cases, rotation and reflection symmetry give 20 different collision cases, where three variants are of the first collision, as discussed in the previous slide, 2 of the second collision, 12 of the third, and 3 of the fourth collision. It should be noted that the other 44 incoming states remain unchanged after the collision step. In this slide, we have an example showing a simulation of 6-direction lattice gas using a cellular automaton. In this image, the grid size is 2000 by 1000. In Lab 5, we will implement the lattice gas model to simulate the fluid dynamics problem. Okay, this brings us to the end of today's lecture. Thanks for your attention.